So last time we went through different subjects that belong for one reason or another to the field of astroparticle physics. Took a bit historical side, right? I spent a lot of time on this cosmic ray story that started with Victor Hess. And then, well, there is this unresolved problem of the origin of cosmic rays, of whatever energy, by the way, from GeV cosmic rays to the highest energy cosmic rays that are like tennis balls, right? That is the exercises that we did. Then, as a side, trying to solve this cosmic ray problem, people developed the tools of gamma ray astronomy and neutrino astronomy also. But there are new problems that arise like this. We have this astrophysical neutrino signal in the beta electron volt range, which is also of unknown origin now. So then as another branch of astroparticle physics is the story of dark matter that was first noticed by Zwicky. And then it's also an old unresolved problem since already good 70 years or something. We try to either, there are theoreticians who put forward different assumptions about possible nature of dark matter. We try to test this hypothesis in laboratory, or we use this gamma ray astronomy and neutrino astronomy to see some signal from this dark matter with the telescope. And then somehow this dark matter story, it starts in in cosmology. And this is, well, maybe the topic on which I will, the approach on which I will concentrate today. So I will try to introduce this problem of dark matter from a bit another point of view compared to Zwicky. I don't know if you remember what was the story of astronomer Fritz Zwicky.
He said that he was Swiss.
He was proud that he's Swiss. Yes. Well, that's what people notice. I don't know. Then that's all.
That's what I remember.
Yeah, he was doing research at the time when people were not sure that galaxies are galaxies. For them, there were clouds, some blurred stars on the sky. And then the hypothesis was that these blurred things on the sky are either some, I don't know, some collections of stars in our galaxy, or these are remote worlds like Milky Way. He was for the second hypothesis. And then he noticed also that this, if these are remote worlds like Milky Way, they are not completely randomly distributed on the sky. Sometimes there are clusters of them. They like clustering. And he, well, tried to test the hypothesis that, well, of course, our Milky Way is perhaps a collection of stars that are kept together by common force of gravity between them, yes? So he tried to test the hypothesis if these all clusters of galaxies are collections of galaxies that are kept together by collective gravitational field, yeah? Then it didn't work for him because, well, according to his estimates of what should be the masses of the galaxies and how far is the galaxy cluster, well, what is the size of the galaxy cluster, it's all non-trivial things, right? So we don't go there and measure mass of a galaxy. We don't know at which, we cannot put a meter and, well, measure the distance to the galaxy cluster, so we cannot measure its size. But with whatever reasonable hypothesis that he was able to formulate at the time, he found that, well, there is a dramatic discrepancy. So the total gravitational field of galaxies is largely insufficient to keep them together. So it should be either some intelligent design, so somebody just for aesthetic reasons put them on this spot in the sky, to make it nice, or there is some matter that he does not see in his telescope, that creates gravitational field and keeps galaxies together in this galaxy cluster. He coined the term dark matter, yeah, for what obvious reason that dark is something that you don't see with the telescope. Since that time, this story developed. So some matter which was dark for Zwicky is not dark anymore because we see it with different types of telescopes. But the story is not over because still the bulk of the matter in galaxy clusters is of unknown nature. So this is one appearance of the story of dark matter. I will try to show how the story of dark matter appears in the context of still larger objects, or rather object in singular, because I will be talking about the whole universe, okay? And then maybe by the end of the lecture, we will come up with an idea of or what can be this dark matter, also inspired by the story of the universe. Good, so that's the plan for today. Now let's try to construct an argument. So we are talking about the largest object known to us. This is, so if we go back to the story of Zwicky, so we are living in a galaxy. This is a representation of galaxies, right? So every point on this map, this is a real map from a telescope called Sloan Digital Sky Survey. Maybe at the exercises today, you will have a look at it. Again, as usual in astronomy and partial astroparticle physics, the data are available, so you can take a look at them. So at this map, every point is a galaxy if it is green, right? But it is rather a histogram. So then if it is orange, there are many galaxies piling up in some places. So the things that Zwicky was studying were clusters of galaxies like these blobs here. So we know that they exist. They are really collections of galaxies. Then if we look at larger and larger scales, we see that, well, there is, of course, some pattern, but if we unzoom and relax our eyes, we see that, let's say, it's a soup of galaxies, which is more or less, it has no features, right? So there is no real center, except for the center introduced by us, because we observe from this point here. So otherwise, well, don't pay attention here to the redshift, you will understand. So it's really a measure of distance, right? So it's a 3D distribution of galaxies in space, viewed from our point of view. So we see that there is no, well, we are not in a special place in the universe. We can tell that in the first approximation, the distribution is homogeneous. Well, it's inhomogeneous on small scales, but it becomes homogeneous on larger scales, yes? And also we can tell that it is isotropic. There is no preferred direction. By the way, it's an arbitrary slice through the sky, right? So in fact, the distribution is three-dimensional. The same statement is valid also for the full three-dimensional picture, right? Statistically, we can certify that there is no special place and no special direction in the universe around us, okay? That's the first thing that we need to start constructing a model. And then the next thing to know is that this distribution of galaxies is not static. We can understand this because, well, as Zwicky was hypothesizing, the galaxies are attracted to each other by the force of gravity. So we can imagine that, let's say, they cannot stay at the same place, right? Everything moves, maybe in some more or less random way. Looking at this picture, we cannot tell. Actually, it's difficult to tell because, well, even if galaxies would move, we would not notice this on our human lifetime scale, right? So the life of an astronomer is too short. Even the life of cumulative generations of astronomers is too short to see this motion. So now, how can we tell that if the motions are random or they are ordered? Maybe in the distribution there is no special place, but maybe everything is moving to the left or to the right, or maybe the upper part is moving to the left and the lower part is moving to the right, so that all the universe rotates around the Milky Way. We want to measure velocities, right? Maybe at this point, how would we do this in astronomy?
So we would use
The relative
the
redshifts
Z,
of the galaxy.
Doppler's effect.
Yes, we can look at Doppler effect, right? You tell that relative velocities.
Of redshift, or like the relative
Right,
redshift.
so it's already, the hint is given here, that there is redshift. So if something is moving away from us, we need to have some frequency standard, right? Like with the radars on the highway, they do what? They emit in infrared, maybe. What do radars do, by the way? What do they use for? Well, the radars measure the speed of cars without touching them, right? So they perhaps emit at some fixed frequency, then the light, the wave that they emit, I guess they emit electromagnetic wave, right? It's hard to imagine that they don't sound somehow, right? So then the light is reflected, and then it comes back with a different frequency, and we can write that if we know the rule of the Doppler effect is such that E over C will be the shift of the frequency, the relative shift of the frequency. Delta nu over nu is velocity divided by the speed of light. Yes, something like this. So if we, well, for the radar, the designer built in the frequency, right? For astronomical sources, how would we know the frequency standard? Yes.
From the emission line.
Right, we need to observe atomic lines. Either emission or absorption, it doesn't matter, right? Because every chemical element has some fixed pattern of emission or absorption lines. It's like a barcode of the element, right? So it has, it's all cataloged. So if we look at some pattern of lines, we know that there isn't some element present in this galaxy or another element in another galaxy. So we can compare the frequencies. Sometimes these frequency patterns, they are shifted to the red or to the blue, right? And we can use the same formula to know the velocity. Of course, it will be the velocity parallel to the line of sight. Yeah. In astronomy, by the way, we can also measure velocities perpendicular to the line of sight, but only for stars in our galaxy, maybe a little bit further away in satellite galaxies of the Milky Way. What do you think? What do we do for this? That's what we do in our everyday life. If I see this train, Sol, moving, how do I know that it's moving? It's moving perpendicular to my line of sight. There is a component of velocity perpendicular to my line of sight. Why? How do I know this?
Because it's moving to something that is fixed. In respect to something.
In a sense, yes. It's changing angular, well, it's changing direction in my field of view, right? So if something is changing the position in my field of view, I can measure angular velocity, yes. Say by how far it moves in a fixed period of time. And then if I know the distance to the object, I can measure, I can convert angular velocity into linear velocity, right? The distance, the perpendicular velocity would be the distance times d theta over dt, right? something like this. This is intuitively simple formula. Yeah. I would need to know the distance. How do I know distances in astronomy?
Looking at the redshift.
It's a catch, right? Because in fact, yes, the redshift is exactly this. Yeah. Well, actually, the redshift is this. This is the relative change of frequency or wavelengths, right? So we already used it to measure velocities, right? Now I cannot use it once more and tell that no, now I don't like velocities. I tell that it's because of the distance.
Well, there's relative velocities between things, and there's also the Hubble constant and the expansion of the universe.
No, but don't be too fast, right? So we don't know yet the Hubble. Well, we are at the basis of. You cannot do, let's say, it will be a loophole or the circular argument, right? To measure Hubble constant, I measure velocities and distances, but to measure velocities and distances, I measure Hubble constant. Sorry for those who don't know yet what is Hubble constant. So that doesn't work. By the way, some of you go to the course of cosmology, right? Roughly half. So maybe I know this feature, right? Because it's every year like this. So in cosmology, I will repeat some stuff from what you know in cosmology, right? But it will be complementary. In cosmology, you use general relativity to derive some equations about dynamics of the universe, right? I will rather use Newtonian gravity for this. You don't jump on your chairs, tell that, no, you cannot do this, come on, no? Because you know that we cannot use Newtonian gravity to describe the universe. So try to catch me where I'm wrong by the end of the lecture, right? It's a game. So some of the assumptions of conditions for use of Newtonian gravity are violated in what I will tell you, right? But I will not tell you where they are violated. But the result, the curiosity is that the result is the same as in general relativity. I can really follow the Newtonian gravity calculation. I use second law of Newton plus the expression for the gravitational force, and it gives me the right answer. And it also, by the way, gives a qualitative understanding that might be not obvious when you do it in general relativity, because our intuition is more tied to the Newtonian laws, Newton laws, right? Because our world here is like this. We have intuition based on them. Right, so coming back to the distance measurements, how do we do this?
Luminosity.
We can use
do like
standard
this.
candles.
Right, so we can do it with something that we would call standard candle. Like for the Doppler effect, we need standard frequency, right? So if we know some source with a fixed luminosity, we take the light bulb of 60 watt or whatever watt or equivalent 60 watt, and we move it far away. If I measure the flux, I can tell you at which distance is the light bulb because of a relation like this. That the flux is related to the luminosity. So luminosity is measured in, say, joule per second in watts, right? Then if I divide it by the area of a sphere of the radius equal to the distance, it will be something that is measured in watt per meter square, yeah? Or in astronomy, people like ergs per centimeter square per second. They like CGS system. So don't blame me. I will be always slow in unit conversions because my head is, I have CGS system built in, yeah? Okay, so this is one possibility. But how do we get standard candle? It's well, there is no light bulb of 60 watt in astronomy. How do we do
Well,
it?
actually there is. For example, supernovas.
How would you know that every supernova has a fixed luminosity?
Well, not every, but well, they have a typical luminosity, for example, supernova 1A.
No, but how do you know? Well, I would tell you now. You never was next to the supernova 1A, right? So how would you certify that it has fixed luminosity?
Well, we have its model and we know where it happens and when it happens, under which conditions. And well, thus we can assume that, well, they are all pretty much the same with a good precision.
Well, so your statement is, again, there is a loophole in this argument, right? It's a circular argument because to establish this model, in fact, people have used the measurements of distances to something, right? So to construct the model, they already knew what is their luminosity, right? So they fitted the model to some data, right? But before they managed to measure the distance to some of the objects, maybe not the furthest supernova, but some of the objects closer to us. So the idea in astronomy, it's a very sophisticated question because, well, as I told, we cannot go and with the ruler and, well, deal the object, right? We need to guess the distance by the mental force and a bit of treachery, right? So in astronomy, the whole story is called cosmic distance ladder. We start modestly. We start from measuring the distance from the Earth to the Sun. That's already a difficult thing, right? So if you imagine Newton and Kepler didn't know this distance, they derived all the laws of Newtonian mechanics, measuring everything in something that in astronomy is called astronomical units. So their distance from the Earth to the Sun was unity, and all the laws were described in the relative distances, just because they have no way to measure this. It's only in 1761 that people managed to really measure the distance to the Sun in centimeters or in meters, yeah? It was done with if I deviate into the story, it will take me 5 minutes, right? But they did it by looking at the passage of Venus in front of the Sun. So if we look from different positions on the Earth, we would see that the phase of this transit is different. For some people on one side of the Earth, the transit will be mostly over. So the Venus would touch the board of the Sun disk, right? But for people, say, on the North Pole, on the opposite side of the Earth, the transit is not completely over. So then by the change of the angular position of the object, they would sort of, well, we can relate this shift in the angular position. It depends on the distance, right? If we are very far away from the Sun, more or less for all people on the Earth, the phase of the transit is the same. But if we are very close to the Sun, the phase of the transit would be widely different, right? This was the first milestone. Then we learned to measure the distances to nearest stars using the knowledge of the distance to the Earth, between the Earth and the Sun. This is done like this. If this is the Sun, the Earth is moving around the Sun. There is a star somewhere there. If we look at the stars, say in spring, it appears in this direction. So it's always the same trick. It's always shift of the object on the sky. We repeat the measurement in autumn. The direction is a bit different, right? With respect to this reference direction. This is vertical on the picture. So all these nearby stars, they are moving small circles on the sky because of the motion of the Earth. So relative motion of us with the star makes it dense on the sky, right? So then we can relate this angle that is called parallax to the distance, because if we know this is 1 astronomical unit. So then this distance here, distance would be astronomical unit divided by theta, something like this, yeah? From the triangle, this is the right triangle here. By the way, this is the origin of the astronomical name for the units, the distance from the sun and between the sun and the earth is called astronomical unit, and the distance to the nearest star is by coincidence, it's about 1 parsec. So the star makes a circle of 1 arc second on the sky. Yeah. So we measure the distance in parsecs because, well, that's the way how we measure them with the parallax. Notice that we need to know the distance from the Earth to the Sun for this, right? Then we tell that, well, like this, with this parallax, there is now a satellite called Gaia, which is able to do parallax. It localizes the stars very precisely on the sky. It is able to measure the distances for all the stars across all the Milky Way, right? So we have a 3-dimensional picture of the Milky Way thanks to Gaia. Then in this Milky Way, there are some stars that are sort of, well, a posteriori, when people started to measure distances, they found that some stars are really always the same. Some stars are standard candles, really. That's how the notion of the standard candles appeared. So there are some notable standard candles that are called, for example, Cepheids, whatever they are. So some special type of the star. So then we tell that, now, well, we look at the Cepheids. We don't need this parallax sync. We can observe Cepheids in a nearby galaxy, Andromeda. Okay, so then we use this relation to establish the distance to the Andromeda galaxy and some other nearby galaxies. Then suddenly in these galaxies, sometimes there are supernovae exploding. Supernova are special, well, types of stars that become very bright for a short period of times. So then people indeed notice that some of the supernova are sort of standard candles with a little bit of effort. And then this supernova we observe very far away, so we can measure distances to the galaxies that are gigaparsecs away from us. So that's how, well, we know distances without touching, but notice everything starts from this distance, right? So it's a ladder. If we make a mistake here, this mistake propagates to the furthest distance measurements. So we have our ways, right? And when we know the distances, we can measure velocities, right? So we can start to see if this distribution of galaxies is static or not, yeah? If it moves randomly or there is some ordered motion pattern. This is the second ingredient that we need in our model. It happens that this motion pattern is not random at all. So in fact, we are in the center of the universe. It's a good news, right? But the bad news is that all galaxies are, for whatever reason, they are scared, they are escaping from us. And with the velocity, which is higher and higher, with larger and larger distance. Move to this, so the galaxies around here, they are moving away a little bit, right? But the galaxies around there, they are really scared. Their velocity is really large. And there is even a scaling relation like this. If we take velocity distance, so all the galaxies accurately line up along some fixed line, we can measure this velocity. It will be, it's written here. So the velocity will be for a galaxy at a reference distance at megaparsec. By the way, megaparsec is more or less the distance to the next to us decent galaxy like Milky Way. It's called Andromeda, right? So closer to us, there are smaller distance, smaller galaxies. Well, so for a reference Andromeda distance, Andromeda is supposed to go away from us with the speed 70 kilometers per second. It doesn't do this because we are forming bound system with Andromeda. So we are circling one around the other. But the galaxies at 100 megaparsec distance would go with the velocity 700 kilometers per second away from us, right? So something like this. Now, if it's not weird, this is surprising, right? That was a surprising discovery by Hubble. The astronomer called Hubble, who was named Hubble. So the constant of proportionality between velocity and distance is called Hubble constant. And then, well, soon after they discovered this relation, the explanation was found that is somehow less, well, it's comfortable for us because like this, we are not responsible for anything. We are not finally the center of the universe. So the explanation for this pattern is like this. In fact, all the galaxies, the distances between all the galaxies increase. We might do or try to do, if you want, an exercise like this. You do the Galilean transformation of velocities, so now we measure velocities from the point of view of the Milky Way. But if you put the center, the reference point somewhere at another galaxy and try to recalculate the velocity pattern, you will surprisingly find that all the galaxies are moving away from this galaxy in the same linear way, right? That's the peculiarity of this linear scaling. So the usual analogy is that if you take the East duff, right? So the pâte à raisin with raisins, right? You take this pâte à raisin, you leave it in the warm place, it will start to grow, right? And all the raisins will go away one from the other. Actually, with velocity, that is proportional to the distance between them, okay? That's so there is a peculiar pattern of this distribution of galaxies that, well, it is, the universe is like breathing, it's expanding overall, yes? So we can try to describe this expansion, maybe, well, I put the slide here, but it's also nice to have it explained one by one, line by line, yeah? So if we, well, let's try to make a simplistic model, like toy model of the universe. We tell that the universe is the gas or soup of galaxies. And let's put that's the reference, the center of the reference frame at some point. And let's count all the galaxies inside some sphere of the radius r. Well, if the density of the galaxies is rho, galaxies, well, grams per centimeter cube or solar masses per megaparsec, whatever, yeah, we can tell that the mass inside the sphere is rho times 4 pi over 3 r cubed, right? And if I take a galaxy somewhere just at the border of the sphere, somewhere here, this galaxy will feel the force of gravity, which will be F equal to g Newton mass times the mass of the galaxy divided by r square, right? Yes, no? Those who follow general relativity, you try to catch me, right? All agree like this. All the galaxies outside, they don't matter really. Or they do. Oh, this galaxy, it attracts this galaxy, no? But I somehow gently ignored it. Why did I do this? So there is well, there is a theorem that tells that if we take a spherical distribution of matter and calculate gravitational force of gravity inside this sphere, it is everywhere zero. You know this theorem by intuition, maybe, because in electricity, there is Coulomb force that has the same dependence on the distance as the gravitational force, right? So we know that we can screen something from, well, the electric field inside a sphere is 0, right? You can check this. If you take the integral over the sphere, you sum all the forces, they will compensate, right? In gravity, there is a theorem like this also, yeah? So it's okay, I'm safe. I can tell that this is the force of gravity. So in principle, if I leave this galaxy unattended with 0 velocity, it will fall to the center. Okay. Now, of course, it would not fall to the center if it has some kinetic energy, right? If it has some velocity. If I launch it with here, it will start circulating over circular orbit, right? Or if I launch it in this direction, it will go a little bit and then fall back, or maybe go to the infinity, depending on the ratio balance between kinetic energy and potential energy, right? We know that for gravitating system, we have this law of conservation of total mechanical energy, right? So it has potential energy, which is G M M over R, and well, it has kinetic energy, which is M V squared over 2. And if we want to model the expansion of the universe, let's assume that the motion is purely radial. So the velocity is dr over dt. It is in the radial direction, and let's call it r dot. Yeah, there are no other components of velocity. Okay, so now everything depends whether kinetic energy is larger than potential energy. Potential energy is actually negative, right? Here there is a minus sign. So if the sum of the kinetic and potential energy is larger than 0, the galaxy will go away to infinity, right? Finally, it will slow down because of gravity, but it will reach infinity. If the sum of the kinetic and potential energy is smaller than 0, then the galaxy will go up and then fall back. Yes, that we know from everyday experience. If I throw this, I have thrown this with velocity which is smaller than the escape velocity at my position, right? That's why it fell back. If I would throw it with about 10 kilometers per second, it will easily go to infinity. Okay, so that's what I wrote here. This is this. Is there a pointer? There was a pointer last time. You see? Oh. Yes, so that's what I wrote here. I wrote the energy conservation law. So kinetic energy plus potential energy is to total energy. I forgot E by convention here, but it doesn't matter. And then I rewrote it for the radial motion like this. And by the way, I divided everything by mass of the galaxy, leaving only, well, this is another constant, right? It doesn't change in time. Now, what did I do next? Yes, I re-expressed mass as through the density, right? Through this formula. And it gives me this change from here to here. And then to make it nicer, I don't know why it is nicer, but I divided everything by r squared to isolate this combination of pi g over 3 times rho, right? But then if I divide everything by r squared, I get here r dot square over r squared. And it gives me an equation. And then I put this potential energy to the right. Yeah. So it gives me an equation r dot square over r square is equal to 8 pi g over 3 rho plus this total energy of m over r square. Well, I put this in gray because, well, I have an intuition as an astronomer that we have one universe, right? So in our case, this term is approximately 0, or maybe exactly 0. Actually, we are not sure. It's some coincidence or fine tuning, right? So if we throw something with velocity larger than the escape velocity, it goes to infinity. If we throw smaller than, well, actually, yeah, if smaller than the escape velocity, it falls back. But we can also fine tune. We can do borderline. We throw in such a way that the thing stops at infinity. The velocity would be 0 when it reaches infinity, right? It's difficult to arrange, right? If I throw this chalk, either I throw it so that it really flies or falls, right? But for whatever curious reason, which we don't know, it's called cosmic coincidence problem. We are in this, no, it's not exactly cosmic coincidence problem, but there is a fine-tuning problem in our understanding of the universe. We think that we are in this borderline situation that we are zero total energy. So it's like we live a little bit of what's it called, thrill, right? Or suspense. We don't know if our universe will recollapse finally or it will expand forever. Yes, but well, those who go to the cosmology course, you recognize this equation. If I change my notations a little bit, this is called Friedmann equation, right? And I derived it without using general relativity. In Newtonian gravity, Friedmann equation is the energy conservation law per unit mass, yeah? Then you also recognize, by the way, this term in general relativity. You have seen this term in the Friedmann equation.
Cosmological constant?
No, this is called curvature term. It's a nice effect for whatever reason in general relativity. Here the term appears as this total energy larger than 0 or smaller than 0. In general relativity, it has some geometric meaning. For some weird reason, in general relativity, the universe, the fate of the universe depends on the shape, its shape. Yeah, if it is a three-dimensional Euclidean space like our own around us, we think that we are living in a three-dimensional Euclidean space. It is in this equation in general relativity comes with E total 0, yeah, or a Euclidean space. But if we are living in a three-dimensional sphere, it corresponds to the E total smaller than 0. So three-dimensional spherical universe would recollapse. And there is also an analog of three-dimensional sphere, which is with negative curvature called hyperbolic space. So in this case, it would expand forever, right? We will not go into this, but it's just for curiosity, right? So to make a relation to this. And indeed, in general relativity, it's not that it's imposed, but since, well, people wrote equations of general relativity from their head, so when they were playing with what should they write in equations, they found that there is no reason why this Friedmann equation cannot have additional constant term. It comes like this. It's really called cosmological constant. And actually, Einstein, when he wrote the equations, he proposed this cosmological constant because he was worried that our universe would recollapse. So he wanted to save the mankind. And he proposed that maybe there is a cosmological constant so that all this soup of galaxies stays still. Because he did research before Hubble, so he didn't know that, in fact, the soup of galaxies is expanding, right? As a matter of fact, we know today that, well, the dynamics of this expansion seems to be such that indeed there is a small but non-zero cosmological constant. And it's actually a problem. Well, this is, well, the problem called cosmic coincidence problem, because now also another fine-tuning problem in cosmology, because I tell that it is this constant that we can add here in general relativity, it's small but non-zero, and it's not naturally small. If I would be say trying to estimate this from common sense argument, I would put there a number that is 100 orders of magnitude larger. And well, it is small, but well, it's playing the game, right? It doesn't destroy. If I would put here something that is 100 orders of magnitude larger, the expansion of the universe would be 100 or 10 times faster, right? So maybe the whole history of the universe would be over by today, right? But somebody also designed the things in such a way that we are still here. So we are not suffering from too rapid expansion of the universe or too fast collapse of the universe. Yeah. Good. So it's for this equation, it's called Friedmann equation. Yeah. Another. Yeah. And by the way, here is the dark matter. I can do order of magnitude estimates based on Friedmann equation. What do I think? What do I see here? On the left side, I see some quantity that is measured in 1/2, right? So it's a rate or frequency. Yeah. Let's look at this coefficient here in this equation. This is the coefficient that is the coefficient of proportionality between velocity and distance. By dimensional reasons, it is something that is measured in 1/2. It's only for convenience that here it is written kilometers per second divided by megaparsec. Yeah, it's it's a mnemonic help. Yeah, a galaxy at the distance of 100 megaparsec would move with 7,000 kilometers per second. Yeah, so like this, it's a quick estimate. But in principle, megaparsec is the measure of distance, kilometer is the measure of distance. So the dimensionality of this is 1/2. And since I already named one constant h0 and the other constant, the other thing I named h, so I have no choice. I have to tell that this is that thing measured. H0 is, well, this h is a function of time. Yeah, so I would tell that by intuition, h0 is h today. Okay. If I, well, actually, this is a correct mapping, because if I would think back, what are the velocities of the galaxies? They are, h is actually the velocity divided by the distance, right? So it is actually the coefficient of proportionality between velocity and distance. So if I plug in this equation, instead of h, I plug h0, I can make an estimate of the density of the universe around us. Yes. This is my estimate. I would call it rho 0. And it gives me something like 10 to the minus 29 gram per centimeter cube. This is a small density. I don't know, again, small or large compared to something, right? So what is our density? What is my density? Yes. 1 gram per centimeter cube. Yes. The density of the air here is 10 to the minus 3 gram per centimeter cube. The average density of the interstellar medium in the Milky Way is about 1 particle per centimeter cube. So 10 to the minus 24 gram per centimeter cube, because particles are protons and electrons are hydrogen, right? So mass of proton is 10 to the minus 24 gram. So this is sort of 5 orders of magnitude smaller than the density inside our galaxy. But it's okay, right? We understand why, because this is the average density of the soup of galaxies. So the density inside galaxies is larger, but there are not so many galaxies per megaparsec. So if we average everything, this would be this number. So it's a tiny density, right? But it is a huge density from the viewpoint of Zwicky and his followers. Because if we play the game that Zwicky was playing, we try to estimate, well, we take all the stars in all in a typical galaxy, we add their mass, we can estimate the mass of a galaxy, right? Then we sum the mass of all galaxies within certain volume here. And we average we calculate the density, we will find a number that is 2 orders of magnitude smaller. So it's a huge density that we don't know how to explain. It's exactly the same problem as Zwicky found, but he found it for one single cluster somewhere. I don't know which one of them is the Homa cluster that Zwicky was studied. Maybe it's not here, by the way, but it doesn't matter. Now, the same problem is found at the scale of the whole universe, not the whole universe, our neighborhood, right? That's, well, how it's a bit more mathematical way to find this problem of dark matter, okay? Maybe let's make a break. You asked for a break, right? All right, in the middle of, so I will switch a bit to the next. So this is sort of benchmark, right? So now you know what is the problem of dark matter. So what do? We do 5 minutes, 10 minutes, 15 minutes, half an hour break. What? Is there, by the way, is there a formal statement somewhere? How long should be the break?
Like normally 15 minutes, you make like on the schedule, like you start on 8:15,
Yes.
you end on 9, and then you restart on 9:15. So that's the formal.
And 9:15, and then I go till 10.
10.
Okay. So I want to bargain. I propose 5 minutes. What's your bet? 5 minutes or 10 minutes?
In 5 minutes.
7 minutes and a half break. Okay. Then we come back at 9:17 and 30 seconds.
Bah, c'est un peu ça. Genre, tu peux essayer de faire exprès, j'étais là, ok, laisse tomber. Ouais. Un peu chaud, oui, sur le point. La moitié, genre, je m'adressais à tout le monde, du coup, je disais vous, et après, genre, je disais, on me perd du milieu, et je disais, je vois, tu te dis, tu te dis, à qui on va parler prénom.
Still one person missing. Oh, okay. Good. So this is the first, our first exposure to this dark matter problem. Maybe before I move on to solve this problem by the end of the lecture, let's make. I want to still advance a little bit with this dynamics of the universe. You notice that this Friedmann equation, it's a differential equation. It's ordinary differential equation that allows us to find the function r as a function of t, right? Time. Then maybe it actually relates function r to another function of time, that is rho, right? So in fact, we cannot really solve it because rho is another function, right? We need a system of differential equations, two coupled differential equations of r and rho to solve it, right? In general relativity, in your cosmology course, you will see another equation that appears there under the name of stress energy conservation, something like this. Without a general relativity, you can derive this like this. If you take the first law of thermodynamics, but without the part that is heat release. Yeah, so this is my first law of thermodynamics here. Change of internal energy is equal to the work done by the pressure. In general, there is plus Q, think in the first law of thermodynamics. But there is no Q here. There is no contact with thermal mass or whatever. So the heat does not go away from the system. It stays in the system. So there is no Q that is lost. Then I may rewrite it like this. So what is this change of internal energy? Or the internal energy, I will take all the energy available in the system. So imagine that this rho is the energy density. I can talk about energy density of mass density interchangeably. I multiply, if it's non-relativistic matter, I multiply by c square, or I don't multiply, so it will be the energy, right? So the energy density in the volume of within the sphere of the radius r, this is my internal energy, right? It changes in time, so I write d over dt. Then on the right side, I have pressure, and I just have the change of the volume here. And the change of the volume of the sphere of the radius r, right? So I isolated my sphere, and I consider the first law of thermodynamics for this sphere, right? Then with a couple, so I can open the brackets here and there, and then this would give me, so I need to take rho dot, then times, this is the composite function, right? So I will have a part with r dot and rho dot. After some rearrangement, I arrive at an equation like this. Rho dot is equal to -3 r dot of r. We recognize this h, which is expansion rate. And in the brackets, I will have p plus rho. So this is a differential equation on rho that comes as stress energy tensor conservation in general relativity. So now I have a system of two differential equations on r, rho, but unfortunately I introduced a new function, that is p. Pressure is also a function of time, right? I need to do something with this. to close this system of equations, we know, right, that the pressure is often related to the density somehow. We know that the pressure of ideal gas, T, is equal to N K Boltzmann T, something like this. N is the number density of particles, so it's rho divided by the mass of particle. Yes. So this is an example of equation of state. Maybe I write it like this: K Boltzmann T over M E. So particle. I like this rho C squared or C squared. Square. Rho. Rho is the actually, yes, if rho is the energy density, right? So then I need to write like this. I divide by the energy of every particle. So then it gives me something of this sort, right? I rearrange the term to highlight this, that T is proportional to rho. And for ideal gas, the proportionality coefficient is K Boltzmann T over MP of mass of particles C squared, yeah? In this room, this factor is a tiny thing, right? Because in this room, temperature is 300 Kelvin or something. Typical energy, kinetic energy of particles, if you take K Boltzmann, is something like 10 to the minus 4 electron volt per Kelvin. Then at 300 Kelvin, the energy of kinetic energy of particles is about 0.03 electron volt. And we are comparing this with mass, the rest energy of particles. For protons, this is giga electron volt, right? So in this room, this is a tiny factor. Well, we can tell that this is approximately 0. But if we take relativistic particles, we would sort of have a coefficient of the order of 1. So different, well, we will see on the next slide that at different times in the history of the universe, we should take either this or that. So in general, we tell that this is some coefficient W. And we write like this, yeah? So then we will see that it's some naive equation of state. Maybe it's valid, maybe it's not valid, but we are still doing toy model of the universe, so we can start with this already. Like this, we have system of 3 equations for 3 unknown functions that we can solve, right? You will see people routinely solve it for some situations here and there. And in the dynamics of the universe, there are not so many possibilities to play with. So everything is, of course, coded in Python. All the equations are already solved and so on. You will see in the exercises section that you, in Python, you do from Astroparticle cosmology load some type of cosmology, which means that, well, some it's mixture of different types of matter with different equations of state, and you tell you press the button and it gives you a solution of these differential equations. You will see a couple of them in the exercises. Okay, so it was yeah, for example, yeah, if I use this equation of state W equal to 0, I can solve the equation, the system of equations straight away. If my W is equal to 0, so P is equal to 0 here, I can write as an example, yes? I would rewrite this equation rho dot equal to -3 R dot over R rho. Then I will divide everything by rho. And then I will integrate over time. You can see that this is logarithm of rho is equal to -3 logarithm of R plus some constant, right? And if I exponentiate it, I find that rho is proportional to 1 over r cube. This is some trivial thing, right? If I keep the number of particles fixed within some fence here, if my volume expands, the density of particles decreases as 1 over volume. Yes, so I found some, well, it's a sophisticated way to express some trivial fact. So then if I use this scaling, I can plug this scaling rho going as 1 over r cube into this equation. This equation would also be easy to solve. I chain with the Friedman equation. I would tell that h square, which is r dot square over r square, is equal to 8 pi g over 3 rho, which is some constant divided by r cube. Then I can cancel the powers of r. I would rewrite it. No, sorry. I would first take the square root of it. No. I would cancel the powers of r, then take the square root of it, right? So let's denote this with some star. So I would write r dot square is equal to the star divided by r. Then I take square root. And then I would put r 1/2 to here and integrate over time. That would give me something like r to the power 3/2 is proportional to t. Yeah. Or r. Yeah, you follow me. R scaling as t to the power 2/3. Yeah. This is a function. Something like this. R e. It's convex. Okay, if I forgot which one is right. Some function like this. What is noticeable that this function crosses 0 somewhere. Yeah. So there is really a point in the history of the universe when the distance between galaxies was 0. It would be, I took an arbitrary r, right? By the way, since it's an arbitrary r, people in cosmology usually talk about scale factor, because no matter what distance scale changes in the same way qualitatively. So all distance scales were 0 at some moment in the history. That's a remarkable moment called Big Bang. Yeah. So everything started in a Big Bang. We can actually do a quick estimate of what is the time from the Big Bang today. For a quick fix, people usually talk about Hubble time. You notice if my Hubble constant is measured in 1 over second, right? If I put it in denominator, it gives me a time scale. It's a notion of bits. T h is equal to 1 over h0. If you do correct calculation with whatever type of matter you like, yeah, you will find that the final answer will be th times some numerical factor of the order of 1. So if we do this estimate, we find some number which I'm not sure if Vladimir has planned this as an exercise, but try to do this yourself. Or maybe you know everybody the answer, right? Because that's some fundamental fact of life which even kids know. Yes, no? Trying to provoke you.
14 billion.
Yes, something like this. Yes, if you are sort of from previous generation like me, maybe watched the Big Bang Theory. So then it's mentioned in the song, right? So they tell 14 billion years ago expansion started. Wait, and then so on. Yeah. Good. So it will give you something like 10 to the 10 years anyway, right? Because we are not so precise if we do 1/h0. Good. So this gives us an impression that with this simple set of equations, we are already able to make a decent understanding of what's going on with the universe, how it started, how it will end, right? Let's mix a little bit into this history because remember I introduced this problem of dark matter. Let's try to understand what's going on in general. Perhaps if there is dark matter, maybe we can find some hints of its presence here in the universe today. We find it, yeah. Maybe earlier on, it made some dramatic impact on something. Let's try to dwell upon this. I will mix a new ingredient that will help us along this way. So this ingredient will be the story of radiation in the universe. It happens that that the universe is filled with thermal radiation. It was discovered by accident, actually. It's a nice story. Two gentlemen got Nobel Prize for this. They were trying to recycle some military antennas left from World War II to do astronomy. And then, well, they calculated what should be the sensitivity of their telescope. Well, it's a radio telescope, or it's a millimeter wavelength telescope. Then they found that their estimates of the sensitivity do not match the real performance of the antenna because they cannot get rid of a noise in the antenna. So then they tried to improve their setup. So something was wrong with the receiver or with the installation overall. There were pigeons flying around who were emitting radio waves or something. So they tried to do whatever they want. They could. They didn't manage to get rid. So they reported this, that there is some noise, which of no explanation for us. But then there were some theoreticians that were looking for this noise. It's electromagnetic radiation that goes in all directions. They were inspired by these ideas of Gamow. I mentioned him briefly in last lecture. He was doing completely unrelated thing. The Gamow was theoretician. He was trying to explain the chemical abundance pattern of stars, right? He didn't manage to do this, so he invented that the whole universe was working as a star. But if the whole universe was working as a star in the past, it means that it was emitting electromagnetic radiation. Yeah. So according to this, if you follow this idea, you have to assume that the whole universe is filled with electromagnetic radiation that is left over of this ancient star, right? So they were theoreticians exploring the ways how they can detect this leftover from ancient star. And then they matched with these observations. And well, nowadays we know that the whole universe is filled with radiation that is called cosmic microwave background. You can notice these are real measurements. It's almost a perfect black body radiation with Planck spectrum. It has a temperature. And well, that's what should I tell? Yeah, it's a new ingredient in the content of the universe. So there is this soup of galaxies, but there is also there are also photons flying around in all directions, right? Photons, radiation also has its own energy density, right? So let's try to look of what would happen if I would consider what is the fate of these photons. I come back to these equations, but now I take radiation. So for radiation, it's a black body gas. I did it more simple way here. Right, so let's not solve the equation, but let's look at the radiation. So this is a black body radiation. with fixed temperature for black body, we know that we can calculate what is the number density of photons, right? We will find that for this black body radiation, there are about 400 photons per centimeter cube. It's actually everywhere around us, also in this room. There are, in every cubic centimeter, there are 400 photons left over from the Big Bang. But then for black body, we know that the number density scales as temperature cube, yes? On the other hand, for anything expanding together with expansion of the universe, we know that this density of photons should also scale as 1 over volume cube, right? If we make a match, I'm making a shortcut, you can do it in a more rigorous way. But comparing this to this, we find that we expect that this temperature does not stay constant. It decreases with the expansion of the universe. So if R grows, the temperature decreases, yeah? More or less in this relation. Temperature scales as 1 over the scale factor, yeah? So today, the black body is 2.7 Kelvin. Well, if we wait a little bit, it will be colder, right? But in the past, it was hotter. That's how it worked. So somewhere back in the past, the universe was working as a star. It was perhaps emitting as a star. Our sun has temperature of several thousand Kelvin, right? So we can find a moment in the history of the universe if we go back by how much? If we shrink the universe by a factor of 1,000, we will find that the temperature was 2,700 Kelvin. That's like a star, yeah? That's a nice match with this idea of Gamow. So then it has a deep implication, right? So now our universe is expanding and we find that it was sort of hot in the past. So it's the theory of hot and cooling universe. It was even dramatically hot in the past. If we still, well, at this page, I solve the equation, this energy conservation equation. If you do the solution, you will find that for the black body, by the way, the equation of state, black body gas is made of photons, right? So these are relativistic particles. If we come back to this equation of state, I told that for relativistic particles, this W sync will be about 1, right? For Planck distribution, W is exactly 1/3. So it's comparable to 1. I need to solve this equation for 1/3 equation of state, W. I will find that the energy density of radiation goes as 1 over R to the 4. And for the gas of galaxies, which is non-relativistic matter, you remember that the density goes as 1 over R cube, yes? Because, well, that was the solution for W equal to 0. So if we trace back in time, today, you can do a calculation, I will not do it now. So today you will find that the energy density of radiation is much smaller than this 10 to the minus 29 gram per centimeter cube. But it was not always like this. Somewhere back in time, it was the radiation that was dominating the energy density of the universe. So nobody cared about dark matter or whatever, because well, the dynamics of the universe was governed by this black body gas of photons. There, if we trace back, this moment of equality between the matter and radiation energy density is naturally called matter radiation equality. And before this moment, it was always the photon gas which was providing a major contribution to the density and pressure, actually. In this, if we would write second law of Newton for that period, we would rather consider photon gas, yes? This is one fact to notice, and the other fact is even more interesting. If we try to go back in the history of the universe, now, well, this is a chapter slide that is called thermal heat. I can build a story now. My toy model is advanced enough so that I can invent some nice tales about what happened in the universe. So today the universe is boring, right? Because what is 2.7 Kelvin temperature of photons is in the microwave band. The whole radiation is called cosmic microwave background. The energy of photons is 10 to the minus 3 electron volt, the average energy. And these photons do nothing. They can heat us a little bit, right? So we are in a microwave oven. We can feel warm a little bit, right? But these photons would not destroy atoms, would not do harm to any tissue. So well, they are completely harmless, right? If we go back, so we shrink the universe by a factor of several thousand, or maybe let's shrink it by the factor of 10 to the 4. So from 2.7 Kelvin, we go to 27,000 Kelvin. And average energy of photons goes from 10 to the minus 3 electron volt. It becomes 10 electron volt. That is bad enough. Why is 10 electron volt photons harmful? By the way, this would be the ultraviolet domain, yes? Why ultraviolet is bad for us? No, it's good for us. It makes us a nice brownish suntan. Yeah. So, well, people living at the time when it was the universe was 10,000 times smaller, they were all nice with nice sort of color of skin, right? Because they were permanently exposed to cosmic ultraviolet background. And so what's bad about 10 electron volt scale?
You can destroy your kinetic.
Right, because well, we should think we should compare this scale with something, right? So something would be the binding energy of electrons in atoms, yes? So to ionize hydrogen, we need 13 electron volt. Maybe some of you remember this. So then means that if these ultraviolet photons would bump into hydrogen, they would destroy it, right? Of course, if they bump into DNA, they would destroy it as well, right? So there was no DNA, no complex molecules, no even atoms before that moment, because collisions between photons and matter were ionizing everything. So somewhere starting from this is the moment when natural atoms form, photons uncouple. So this is the story of the universe told in the forward direction, right? If I go in backward direction, I would tell natural atoms are destroyed. And well, the matter in the universe from neutral becomes sort of, it goes into the state of plasma, right? So there are free protons, free electrons that are flying around. And actually the universe looks like a star, because that's the state of plasma inside the sun, state of matter inside the sun, it's plasma, ionized, right? For the same reason, because inside the sun, the temperatures, actually the temperature inside the sun can reach millions of Kelvin, right? The surface of the sun is thousands of Kelvin, but inside the temperature is even higher. So everything is ionized inside the sun, yeah? So the universe was indeed like a giant star without boundaries. So all, everything around was like inside the star. Then let's be more dramatic. Let's go still, let's shrink the universe still by another 6 orders of, no, another, what? It's another several orders of magnitude. Well, what matters, I want to bring, so at that moment that we consider, the typical energy of photons was about 10 electron volt. Let's try to squeeze by another 5 orders of magnitude so that it becomes mega electron volt. There is something special also about mega electron volt scale. What is this scale? You'll find it in when we are talking about nuclear energy. Typically, a nuclear power plant, what does it do? It works on fission of uranium nuclei, right? When they decompose, they give some energy, and typical energy per reaction is in the mega electron volt range, because this is about the binding energy of nucleons inside atomic nuclei. So before 10 electron volt was the scale of binding energy of electrons in atoms. Now we are talking about the energy of the link between protons and neutrons inside atomic nuclei. If the temperature of matter is such that the typical kinetic energies are in the mega electron volt range, collisions between particles would be destroying atomic nuclei, right? It's worse than than before. Yeah, before only atoms were destroyed. Now there are also nuclei destroyed. So then maybe this is another moment in the history of the universe. It's called Big Bang nucleosynthesis. Remember, this picture goes, suppose that we go in forward direction, right? So before there were no nuclei, and then as soon as the universe cooled below mega electron volt, suddenly nuclei appeared. And then if we go still back in time, they will be worse, right? So when the temperature would reach 100 mega electron volt, even protons and neutrons would be destroyed. So it was a soup of quarks and gluons and other stuff, and so on, right? So I would not tell what was still before. It gets worse and it gets worse with if we go back to the Big Bang moment, right? So in principle, the temperature grows in unlimited way. So that's a general impression of what happened in the universe in the history. Let's try to find the dark matter here. So if I go, say, yeah, maybe if I go back to the moment when there is one thing to add here. If I go to the moment when typical energies of particles, so temperatures were around 10 to the 10 Kelvin, 10 billion Kelvin, typical energies of particles were mega electron volt, I can notice that mega electron volt is also 2 times the energy, rest energy of electron, right? So I would imagine that collisions between particles were able to produce electron-positron pairs. So if I'm before this moment, I would think that the particle content of the universe was richer. It was full of electrons and positrons because they were produced and destroyed at will. So perhaps positrons went into thermal equilibrium because, well, collisions between particles establish thermal equilibrium, right? If I go to 100 mega electron volts, I would tell that perhaps still other bunches of particles were produced and destroyed. So actually, early universe was a soup of particles which were all in thermal equilibrium, produced or destroyed in the measure of necessary. Among those particles, I would even find particles which I would never see in telescope. Among known particles, which particle I would, well, which particle would not give me a sign in the form of photons? So electrons can emit photons, absorb photons, right? Protons and neutrons can also do this in their collisions because they are electrically charged particles. Photons are quanta of electromagnetic field, yeah? But what particles are not charged with respect to electromagnetic interactions? Neutrinos, right. So what about neutrinos? Were they created or destroyed at will? Perhaps yes, if this was like this. Then if we follow the history of the universe, we maybe find that, well, there is some leftover from the Big Bang, like we have this leftover in the form of photons. if there is a leftover in the form of neutrinos, that's a perfect dark matter. I would never see it in the telescope, right? Because by definition, they don't produce photons, but they exist. We even know that they have mass, right? So they are dark matter in a pure sense, right? So by definition. Let's try to see what happened to them quickly. Yeah, I go to this moment. You see, it's even marked neutrinos decoupled. So how, it also tells us what happened to them. So before this moment, they were in a sense coupled, and after this moment, they decoupled. Yeah, let's try to understand what does it mean. Decoupled doesn't mean disappeared, right? So it's an encouraging sign. Yeah, somebody wrote this for us. So maybe they are around us today. Let's try to see. So what does it mean, coupled or decoupled? Usually, if we are in particle physics settings, we can say that something is coupled if the particle interacts with other particles, right? That's the sense of the word. And how we tell that if a particle interacts with other particles, way to formulate it somehow mathematically is to tell that the time before next interaction is shorter than the characteristic time scale of our system, yeah? Here we are in the universe, right? So let's be simple. Let's define it like this. Try to follow the definition. So the particle is coupled if the time to the next interaction is shorter than the current age of the universe, yeah? Or current Hubble time scale, yeah? Did everybody follow? That's some logical thing that you need to catch. Then everything is simple. We have some mathematical thing to compute, yeah? So the time, the age, the current age of the universe, let's tell that this is the Hubble time, right? This is a function of time because Hubble parameter, this h decreases with time, so t increases with time, yes? Then what do we compare it with? What is the time to next interaction? Now I'm, a question, general question. Do you know about mean free path? Yes, no? So who is easy with mean free path? No?
Well, we know what it like is in general in physics. Like if there's a particle and it travels before the next interaction.
Yes, so, well, I was talking about time before next interaction. We can also talk about the distance before next interaction, right? So this is the mean free path. Now, this is sort of intuitively easy. Imagine a particle moving through a gas of other particles. So sooner or later, it will bump into another particle. Here, it would bump first into this particle. If it has, the impact is close enough, right? So in my sketch, my particle has a size here, right? So all particles found within the cylinder swept by this, if I take a cross section of the particle, I can make a cylinder which is has the axis along the direction of motion, and the area here, this is the area of the circle here, right? So all particles which will be found within this cylinder will interact, right? And my mean free path, if I know the cross section of the particle, I can calculate the mean free path, the height of the cylinder, in which I would find at least one particle from the medium, right? That's the way to calculate it. So for this, I need to know the density of the medium. If my medium is very dense, well, obviously the distance to the next interaction will be short, right? If my particle is large, the distance to the next interaction will be smaller again, right? Because I am more efficient in sweeping other particles, right? So the formula is very intuitive. I write a formula for mean free path like this, 1 over the cross section of the cross section, I know it's sigma. It's a convention in particle physics. The density of the medium is n, and it's already something of the dimension of distance, right? Cross section is the area, so centimeter square, and the density is it's 1 of particles per centimeter cube. So if I put them this combination in denominator, it makes me the distance. Yeah. Okay. By the way, I'm using this system of units, so I don't make a distinction between distance and time, because neutrinos are very light particles. They travel with the speed of light, and I would measure distance velocities in the units of c, right? So if you see velocity, it's always expressed in the units of speed of light. Okay, so if I do this, I can see the time to next interaction, but I would need to know what is the cross section. And neutrino is a particle that still interacts with other particles, but only through weak interactions. Well, not all of you, well, half of you are astronomers, half of you are particle physicists. So particle physicists would know an expression for the neutrino cross-section. Astronomers would not. So I write it for you here. It's given by some fundamental constant called Fermi constant. And it depends on energy. It's energy square, right? So I could use this expression for the cross-section. I would replace the energy by temperature. Again, I use the system of units. I would, from now on, I will drop this K Boltzmann. Yeah. So I don't make distinction between temperature and energy, right? So I express temperature not in Kelvin, but immediately in energy units. Yeah. So this gives me some scaling, because I could use the density of particles. For radiation, it's temperature cube. Yeah. This is the origin of this temperature cube. The cross section is temperature square. So my time to next interaction goes as 1 over temperature to the 5. When the temperature is high, the mean free path of neutrinos is tiny. They are coupled, right? But then the temperature drops, and at some point they got decoupled because the time to next interaction gets larger than the age of the universe. So if I do the math, I can find the temperature at which this happens. You can follow this later on if you want. There is a moment like this. It happens to be mega electron volt temperature. So before mega electron, well, before the moment when the typical energies of particles were mega electron volt, neutrinos were interacting. They were produced and destroyed in weak interaction reactions. We know a couple of them. We know, for example, that neutron decays into proton, neutrino, and electron. This is an example of weak reaction, weak interaction. Yeah. So there is a bunch of them, and neutrino were in thermal equilibrium in with other particles in the before the temperature dropped below mega electron volt, but then they decoupled. And since that moment, they do nothing. They just exist. And their density is diluted by the expansion of the universe. We can make a prediction how many neutrinos are found in every cubic centimeter around us, the same as for photons. We know that there are 400 photons in every cubic centimeter. There are also about 100 neutrinos per cubic centimeter left over from the Big Bang. That's very cool. So that's really a dark matter that is guaranteed to exist even based on our very naive model of the universe. The only problem is that we would perhaps never detect it because it's difficult to catch those neutrinos. And there is also a small problem like this. We actually know what is the mass of neutrinos. We almost know what is the mass of neutrinos. So if we multiply the mass, well, I will not go into this story of mass of neutrinos. Maybe those who go to particle physics course, you already know, right? What is the mass scale of neutrinos? It's a quick check, right? So where you are in the level of particle physics. It's ridiculously small. It's about, so the rest energy of neutrinos is perhaps around, well, it's smaller than 1 electron volt. Yeah. To compare with the next lightest particle, which is electron is half of mega electron volt, right? So neutrinos are ridiculously light. And unfortunately, they don't do dark matter. If we multiply the known density of neutrinos by their mass, or at least by upper limit on their mass, they would, no, well, so if we would multiply by their mass, they would give us this dark matter scale if the rest energy, again, notice that I drop C, right? So for me, M and MC square is the same. I measure mass in the units of rest energy. Okay, so if the rest energy of neutrinos would be 100 electron volt, that would do the job. So they would be the dark matter. But unfortunately, we know an upper limit on their mass, which is around 1 electron volt. So it didn't work with these neutrinos. It's a nice try. Next time, we will try to trick the story. I will try to patch, to repair this failed model of dark matter, make some nice neutrino out of my mind, yes? So that's what physicists do. They try to sort of guess what should be the particle that is like neutrino, but it's better. It makes us the dark matter. So it didn't work for dark matter, just for information, yeah? But it was a first try, yeah? Just maybe 1 minute I finished that. I told that they are not detectable. But there are people around, I guess even on this floor, there is somebody involved in experiment called Ptolemy, which tries to detect this 100 neutrinos per centimeter cube that are flying around us. For a quick explanation, they try to use the effect of beta decay. I don't know if you, well, if we, the beta decay is something like this. If we, you know that neutron is an unstable particle. If we leave it unattended, in 10 minutes it will be gone. It will convert into proton and will release an electron by electrical neutrality, neutron. So to produce proton from neutron, we need to eject a particle that is negatively charged, right? So it will eject electron, but there is also neutrino ejected, right? Which we don't detect, right? So people use this effect to measure the mass of neutrino, because if there is this beta decay, some nucleus decays into another nucleus with emission of electron and neutrino, electron can carry only energy that is released in this reaction. So this is the difference in the rest energy of proton and neutron minus the energy carried away by neutrino, right? And the minimal energy of neutrino is its rest energy, right? So if we look at the spectrum of electrons coming from this reaction, it will be some spectrum which will be sharply cut off at an energy that is the energy release, this difference of the rest energies of proton and neutron minus the rest energy of neutrino, right? That's how people try to measure the mass of neutrino. There is another process possible. There might be this one of these neutrinos from cosmic neutrino background bumping into an atom and inducing a beta decay. That's called beta decay because beta is electron, right? Particles are named for a weird reason. Like alpha is helium, beta is electron. I don't know why. So there will be this induced transformation of the nucleus because there was a neutrino bumping into it. The energy conservation of this reaction is different. So what is the energy available? This is the difference in the rest energy of proton and neutron plus the energy of neutrino, right? Which is the minimal energy is the rest energy of neutrino. So we would expect, instead of a sharp cutoff in the spectrum, we expect also an additional bump in the spectrum. That is because of this induced beta decays. If we have a very sensitive spectrometer, yeah, we can measure the energy of electrons. We can observe this bump and in this way detect the cosmic neutrino background. This is the idea of this Ptolemy experiment. You can imagine that this is a very tricky machine. So you better ask, I guess it's Lesia Szutska who is involved in this. Ask her maybe. if you are interested. Yeah. So that's for a curious story of. So what did we do today? We tried to understand this problem of dark matter. Now we have some mathematical little understanding of what is it, how does it appear in equations. Then we tried to find if we have a natural candidate for this dark matter in the amount particles that we know. Neutrino would be the good one. We even know that there is a lot of neutrinos in this room that we don't see, right? And then, unfortunately, they don't do the dark matter, but it is interesting to study this cosmic neutrino background.